Well, so which kind of algorithms can be applied to deal with these problems? There are basically two big families. And the first family is exact and complete methods, which try to evaluate all the possible solutions, although they try to avoid evaluating some partial solutions that lead to non-optimal solutions and approximate approaches. In this case, the idea is not to evaluate all the possible solutions, not to try to cover all the search space, but a subset of interesting solutions. And within this family, we find heuristics, which follow an idea to generate good solutions for particular problems, and this is important, particular problems, and metaheuristics, which follow ideas which can be applied to a large family of problems. For instance, in heuristics, the idea of introducing to the knapsack the objects that provide you with the largest profit per unit of weight can be applied only on knapsack problems. That cannot be applied on the traveling salesman problem or other problems. So these particular ideas for particular problems are heuristic algorithms, while metaheuristic can be applied to many different problems. For instance, one idea in one metaheuristic genetic algorithms is to combine the information from good solutions, from previous solution. And this idea can be applied to every problem. You got different solutions and you try to combine this information from previous good solutions. Apart from that, apart from being general ideas, they are used, well, they are faster than complete methods, they are easy to be implemented, and they can be applied to problems with higher complexity, for instance, for designing controllers for systems. When should we use metaheuristics? Well, the question is, if we have a procedure, an algorithm that solves my problem in polynomial time, either quadratically or perhaps, uh, to the third, then we should apply that algorithm. Instead, if we don't have such procedure, then we should go for metaheuristics. Well, which are the ingredients metaheuristics consist of? Well, the basic ingredients are uh, a solution encoding, a way of encoding potential solutions for our problem, a way of assessing the quality of the solutions, a way of sampling solutions, of producing different solutions for my problem, and a stock condition. That means that you are going to run your metaheuristics for a number of iterations or perhaps a budget of computational time or whatever. Apart from that, some metaheuristics have some other components, and other metaheuristics have other components, such as memory mechanisms, the starts, several sampling operators, and so on. Well, the advantages and disadvantages have already been said. Perhaps something that I have not said explicitly is that they are not exact methods, they are stochastic. This means that different executions of the same meta-heuristic will provide you with perhaps and probably different solutions. So in most occasions, you are interested in running your meta-heuristic several times in order to get an idea of how well it behaves on your problem. Here you got several names of metaheuristics. There are much more metaheuristics, uh, many more, such as shark-based metaheuristics, spider-based metaheuristics, monkeys. Well, there are a huge amount of metaheuristics. And this is a classification we are going back in the future. And the basic classification of metaheuristic is this one. Uh, Either they are trajectory-based metaheuristics, which means that they draw a trajectory in the search space, or they are population-based metaheuristics, which means that they evolve a set of solutions for several iterations. Trajectory-based can be think of kind of hill climbing algorithm and hill climbing with memory mechanisms or uh, acceptance functions with other operators. The idea of all trajectory-based metaheuristics is that they start at some point, they evaluate the neighborhood of such solution, and go to another neighboring solution, uh, usually better than the solution before. So they take this step because this fitness value, this quality is better than this one, and afterwards it evaluate the neighborhood of the new current solution, and so on. So they draw this trajectory on the search space. Sorry, in the search space. Well, actually, here I got only just one decision variable, but in many problems there are a lot of decision variables. For instance, in the knapsack problem with 100 objects, there are 100 decision variables. So the trajectory drawn by these kind of metaheuristics in this search space is quite more complex. And this is population-based metaheuristics. Each of these points represents a solution, a potential solution for the problem, and there is an operator that combines this information. There is actually a third family of metaheuristics, which is not usually considered, which are constructive metaheuristics. In this case, let's say that there is a family of agents which step by step construct potential solution for your problem. So the idea is that this is a complete solution, but there are some pieces missing because the agents are adding new pieces in this solution until it is finished, it is complete.